Thank you, Anton. And it's cool to be here hosted by my former students. So it's good to see some of my academic grandchildren. Any of you like thinking of it that way? So this talk, the main system I'm going to talk about is called the gradostat. It's a network of chemostats. Has anybody ever heard of the chemostat? No, not one. That's good. Oh,
sorry.
John. About halfway through
this place.
Yeah, so I just started. The system we're going to talk about is called the gradostat. And the reason it's interesting is, one, it's a nonlinear dynamical system of some genuine classical interest on its own. And also, there are a number of relevant applications that we can really think of as the gradostat plus extra layers of modeling detail. And there's quite a few. In this case, the motivating application is wastewater treatment. For example, you might want to decide where to build new pipes. You might want to decide certain flow rates of pumps or valve positions. And there are some real system level objectives, maximizing energy capture from biogas. So just to spend a couple minutes situating this work in the existing literature, the gradostat has a small but established literature stream, mostly on classical nonlinear analysis, so equilibria, stability. On the application side, there are papers on optimization of wastewater network. And what you tend to see is that there are either papers that just drop the nonlinearity and just solve a linear model that you would say is just the fluid flow, or they leave everything in there and use things like genetic algorithms. And Anton maybe told you how I feel about that. But I don't know them. So the place where this work sits is really digging into the structure so that we can come up with a scalable strategy for when we still have the nonlinear model in there. So our basic perspective is that if we can figure out how to deal with the gradostat and deal with the challenging aspects, then we can work on all sorts of applications by adding on more detail. Target, both because it's scalable and robust, and because it's, well, eventually you just start always doing what you know, convex optimization. So the goal is to come up with a nice convex model that we can use to optimize the gradostat. This was work that I started during my sabbatical at University of Montpellier with Elaine Rappaport, and later also with Denis Dauchaine. And we're continuing to work in this area. So I quite a lot of future work that I see here. So each node in the gradostat network is something called a chemostat. And what a chemostat is, it's a volume of constant water, and it's got water flowing in at the rate Q and flowing out at the same rate. And there's two concentrations we're interested in. The substrate concentration, that's kind of like the concentration of the dirty stuff in the wastewater. And then the biomass are microbes that consume the substrate and in that process increase their own number and therefore increase their own concentration. And the nonlinearity at the core of the chemostat is this here, where mu is called the growth rate, and it's a function of the substrate and the biomass concentrations times the biomass. And together, this term is called the kinetics. Now, the most famous form for mu is the monad function, mono en français, I think. You can see this is basically the simple expression that can capture diminishing returns, where it tops out at mu max and it starts off at 0. So it looks like that. And Contois is basically similar, also a popular function. And instead of just having K there, we have K times X. And we're going to focus on those two, but there are other cases we can also consider. So if we want to model the chemostat, the rate of change of the mass of the substrate is the volume times the rate of change of the concentration. The first term is the substrate that's being lost, that's being consumed by the microbes. Then we've got plus the substrate that's entering from here, minus the substrate that's exiting from the outflow, through the outflow. And we can similarly write a differential equation for the biomass. The only real difference is that now it's gaining mass as a result of the microbes eating the substrate. And Y here is what you call a yield factor. So it's sort of an efficiency. Lots of papers on the chemostat. This is a classical textbook that is pretty authoritative on the subject. So the gradostat is just a network of chemostats where those flows going in and out are actually interconnections between the chemostats. I'm just showing mass flow, but with no loss of generality. You can also have diffusion, and I'm just leaving it out for concision. So if we wanted to write a mass balance for the substrate, say in chemostat 2, well, we've got what's going on in the chemostat. So the mass being lost to the growth, plus what's coming in, minus what's going out. And then we have the network terms. So that's the substrate that's leaving chemostat 2 for chemostat 3. So it's just the flow rate times the concentration of 2. And you would imagine in wastewater, this isn't a potential where you have this concentration minus this. It's just flowing. So there's not really much backflow. But that would be diffusion if we had it. And then we've got Q12 bringing in substrate from chemostat 1 to chemostat 2. And so we can write a general mass balance for the substrate in chemostat K, where we just sum over whatever's going in, or minus whatever's going out, plus whatever's going in. And if we write down similarly a set of the equations for the biomass as well, what we have is our complete model of the gradostat system. And it's a system of 2n nonlinear differential equations. It's very useful, unsurprisingly, to put it in matrix and vector form. That starts with a matrix that in the literature is always denoted M. This is the definition of it. M is, it's easy to think of if you just look at the example. What you have on the off diagonal is whatever's moving between the tanks. What you have on the main diagonal is the total amount leaving each chemostat. So M has some very useful properties. It's what we call a compartmental matrix. So from that, we automatically know that it's negative semi-definite. It's invertible, which is to say negative definite, if it's something called outflow connected. That means that if whichever chemostat I start in, there's a path I can follow out of the system. And it is irreducible, we're guaranteed no matter what that the entries are non-positive, and they are strictly negative if M is irreducible. And that means that we can follow a flow path from any tank to any other tank in the system. Now, wastewater treatment, if we think of that example, we don't want that to be irreducible. We don't want indefinitely circulating sewage. But it is going to be outflow connected because sewage is definitely going to be leaving the system. On the other hand, sometimes a gradostat is used as a discrete approximation to something like soil, where you have microbial activity. And then you would have irreducibility because you've got stuff kind of slowly moving around the whole thing. So this system here, just to get a handle on these concepts, it is outflow connected. Even though there's no direct outflow here, we can follow a path out. But it's not irreducible because, for example, if I start in chemostat 3, I have no way to get back to chemostat 1. So with the matrix M, now we define a few more vectors. F is a vector of the nonlinear functions for the kinetics. S with no subscript is just the vector of the substrate concentrations. Similarly for the other quantities. C diagonal matrix of the flow rates, W diagonal matrix of the volumes. So altogether, this is our vector model of the gradostat. Any questions? I should say jump in at any time. Okay, everybody has a handle on the system. So next part, convex optimization. I made this talk with a like a wastewater treatment, never seen optimization audience before in mind. So everybody here is probably pretty well versed in optimization, correct? So I don't need to spend a lot of time on this, for example. Okay, so just a little motivation for why we want to think about why we want scalability. Well, if we have a collection of plants, and instead of just having one substrate and biomass, we might have 20 substrates and 5 biomasses. And let's say we want to optimize the system over a number of time periods. Well, things can get very big very quickly. It's typical that a time horizon for optimizing wastewater treatment could be a whole week. So we could have 5,000, 50,000, few 100,000. So there's real reason for trying to get large. Yes?
So you didn't set up and describe the optimization objective, right? This was just flow so far.
Yes, so all we've done so far is physical modeling. Convexity is often an important characteristic on whether an optimization problem is hard or not. Convex, not convex, not a big deal in 2 dimensions, but in a few thousand dimensions, you could have 2 to the 1,000 little local minima. So it really can affect our ability to find a good solution to the problem. Similarly for sets, this is a convex set, this is a non-convex set because we can find 2 points where the line between exits the set. Everybody comfortable with these ideas? And so if our objective and all the constraints are convex functions, then we have a convex optimization problem, and that unlocks a lot of very powerful tools. The big 4, I'd say, are linear second-order cones, semi-definite and geometric programming. And really, there's lots of good features. One of the main ones is that we get access to great hands-off solvers, where once we've stated the model well, then we can basically just press play and get our answer. Whereas with non-convex optimization, well, a lot of times they come with sexy sales pitches, but then 4 months of parameter tuning later, you start to think maybe I should have understood the problem better. So in the gradostat, there are 2 non-convexities as just in the model. One, we have these bilinearities between the flow rates and the concentrations. This, it's not easy, but it's very extensively studied, particularly in optimization of chemical processes. You have tools like McCormick relaxations, lift and project relaxations. You have things like alternating block coordinate descent. So even though this is a challenge, I'm going to basically say there are off-the-shelf tools to deal with it. And because of that, for the sake of this talk, I'm just going to assume that the flows are parameters. The other non-convexity that is really the focus of this talk is the one that comes from the microbial growth. So in the case of the monad function, we've got this here. And dealing with these nonlinear growth rates is really what this talk is about. And so our main contributions are going to be, we do find some nice convex structure that enables us to optimize the gradostat at some very large scales. Okay, so now let's actually set up the optimization problem. We could have a number of different objectives, minimizing the outflow of substrate. That in the application is basically minimizing the quantity of untreated wastewater that is being released. That's basically passing through the plant. We might maximize the production of biogas. Actually, under some conditions, these are equivalent, but the production of biogas is proportional to the microbial growth in all the chemostats. Or we might just have a generic convex objective. So I don't want to all of them are fair game. I'll just go with this one for now, since some of you study energy. But really, it could be any of them. We can have a lot of different decision variables, inflows and outflows. We might have some ability to influence the concentrations. For example, if we have biomass recirculation in the plants. We might also have the ability to control flows or the construction of pipes. And then, again, this is for a very non-optimization audience. We have some physical variables that we don't have direct control over as engineers, but that depend on the other decisions. And so they're also variables in the problem. And finally, we might have a whole bunch of operational constraints, such as budget for new pipes, limits on outflow concentrations. These are typically linear. The real challenge is representing the gradostat itself, the physical constraints, which basically we just put in the system model into our optimization. Now, the first thing we do is we make a steady state approximation. We don't actually need this. We can put the dynamics back in later, but for the sake of this talk and the specific analysis we have for this case, for now, I'll go with this steady state approximation. So with all of that, we can go ahead and state our full model of the gradostat. We're maximizing the biogas production subject to the steady state physical behavior of the gradostat. Make sense to everybody? The first thing we do is we make a substitution. We define this vector T, where every element is equal to the nonlinear kinetics in each chemostat in the system. And because we've assumed that the flow rates, which are all in the matrix M, are constants, that means 1, 2, and 3 are all linear, and all the non-convexity is now confined to constraint 4. So if we can figure out how to deal nicely with constraint 4, then everything else is already in place. Okay, let's understand constraint 4. In the case of the Contois growth function, this is what it looks like. Now, this is a nonlinear equality constraint. Nonlinear equality constraints are always non-convex. Consider, for just a simple example, x squared minus 1 equals 0. Well, we can represent that as a x squared minus 1 less than or equal to 0 and 1 minus x squared less than or equal to 0 together. And one of them is convex, and the feasible set is right here in green. And the other one is non-convex, and the feasible set has a hole in it. So that actually points to our strategy, which is convex relaxation. And the basic idea for convex relaxation is we try to divide up the convex and non-convex part of the problem as cleanly as possible. And then we just throw away the non-convex part and hope that we haven't lost too much information. So for example, x squared minus 1 less than or equal to 0 is a convex relaxation of x squared minus 1 equals 0. We can also think of this in terms of sets. So the feasible set for this constraint is just plus 1 and minus 1, whereas the feasible set for this constraint is the interval from minus 1 to 1. So if this is a non-convex set, this is a convex relaxation. And we can talk about the quality of a convex relaxation sometimes in terms of how tight it is. So this is better because we're allowing in fewer points that are infeasible for the original set. So that lowers the likelihood that we're going to end up with a not meaningful solution. Okay, so here is the non-convex constraint we really care about. And our relaxation is just to replace that equality with a less than or equal to. There's some clear intuition for what this means. T is the variable showing up in all of the physical constraints in the objective. So what we're doing is we're saying that the actual microbial growth in each tank is less than or equal to the what you get from the kinetics. Whereas in the actual model, it's strictly equal. It's actually equal to it. So we immediately have two questions. Is there a benefit from making this relaxation? Is it actually convex or just a relaxation? And does it make the problem easier to solve? And two, what is the price we pay? How much accuracy, how much information have we lost from the original problem that we care about? So one of the main ways we can talk about how accurate a convex relaxation is something called exactness. And so basically consider these two optimizations. Here's our relaxation with the inequality. Here's the original problem we care about with the equality. We say that the relaxation is exact if at the optimal solution, this is satisfied with equality. That means that we solved this problem and then we got lucky because this was satisfied with equality. And therefore, this solution is also a solution to this problem. And therefore, because all we were doing was expanding the feasible set in this problem, well, that means that gives us the optimal solution to the original problem. So exactness is kind of the best possible outcome. So we have a theorem that guarantees exactness for our convex relaxation. Let me state the conditions and then I'll discuss what they all mean. Suppose that the gradostat is outflow connected. So that means that's very reasonable, that there's always a route out of the system from any hemostat. And let's suppose that the kinetics are, so this function here are concave, differentiable, and satisfy this inequality. Then the relaxation is exact if either there is outflow from every tank or if the matrix M is irreducible. So let me now discuss this a little bit. This condition here looks a little like it doesn't have much meaning, but it's very easy to satisfy. And basically the reason is that if this is convex, or sorry, concave, okay, that's good. And in most applications, X, the biomass is much larger than the substrate. And so what that means is that this partial derivative is typically on the steeper part of the concave function, and this partial derivative is typically on the flatter part. So this is usually very easily satisfied in all the applications we've looked at. This is just a pair of, these are sufficient conditions that are a simplification of a more complicated condition that's in the paper. Now, let's first come up with some intuition for why exactness is a reasonable thing to hope for, and then I'll give some disclaimers as well. So exactness is quite reasonable to expect because, well, in the objective, we're maximizing T, so we want to push it up. And so why wouldn't this be satisfied with equality? That's going to happen at least one of the tanks. Probably it's going to happen in most of them, even if it doesn't happen at all. And what the conditions of the theorem guarantee is that there's no sort of pathological solution where it can cheat the physics and send some substrate illegally into another tank. So that's why we would expect the relaxation to hold. Now, also the theorem, there's sufficient conditions. So there are other cases where we can get relaxation even when we don't have a guarantee. And what the theorem says to me is, it just says that it's a reasonable approximation. It's not meant to be a rule for when you can apply the relaxation and when you can't. More, it just gives some compelling evidence on the theoretical side that it's probably a good approximation. And we'll see in the numerical results that indeed it does work in practice. So the other side, we've looked at the problem of how much accuracy do we lose. The other side is how much computational tractability do we gain? This is a quick reminder for people who don't work in optimization. Everybody knows the convex, then the negative is concave. Okay. Okay, the monad growth rate. Clearly a concave function, which is what we want since it's on the right-hand side. The biggest weakness of this work is that the monad kinetics are non-convex. This is a quasi-concave function, but that doesn't really help us computationally. Let's think about Contois, however. Well, this was the Contois growth rate. And let's recall a basic, I don't know if we call it a result or something simpler from convex analysis. Consider the function f of z, where z is just a vector of variables, and let's suppose it's concave. Its perspective is a function in one higher dimension defined as t times f of z over t. If f of z is concave, then its perspective is also concave. Now we could make this statement just by taking second derivatives, but I think this is a nice little connection. If we take the perspective of the monad growth rate, not the kinetics, but the growth rate, which we know is concave, the perspective of the monad growth rate is actually the Contois kinetics. So that's good news. The Contois kinetics are concave, and we can see it has a nice concave shape. So that's good news for optimization. Okay, so now we know that the relaxation is convex in two cases. If we say that the biomass is a constant parameter, which is a decent approximation because it tends to be large and unchanging in wastewater treatment, then monad leads to a convex constraint. And the Contois function, the Contois kinetics lead to a convex constraint as stated with no further approximation. Okay, so that's good news. Can we find any more structure in there to be exploited? And the answer is yes. It turns out we can put these in second order cone form. So this is the general form of a second order cone constraint. Has most of you seen this at some point? So it generalizes linear programming. You obtain LP by setting A equal to 0. It's a special case of semi-definite programming. I would say as far as how practical it is, it's kind of like linear programming, not as scalable, but you really can press play for as long as you have even hundreds of thousands of variables. And you can handle discrete constraints, maybe up to 50 or 100 discrete variables. So our next theorem is that this constraint here can be rearranged as the following second order cone constraint. And there's no real technique. The proof is you just square both sides and simplify until you get back to this. So I don't know if it's very transferable to another context. But one of the things I like about this result is if you've ever done research involving second order cone programming, what you typically have is you go into one of Boyd's surveys, for example, and you have a list of 5 or 10 situations that lead to second order cone constraints. And you see, hyperbolic functions or, you can rearrange this as a hyperbolic function. It doesn't look very natural that way, but I would say this is basically a new addition to that list. That really just another thing that has to be eyeballed. This is our second theoretical result. And similarly, in the case of Contois, we can rearrange this as this second order cone constraint. So this is very nice. We have taken our original problem. We've come up with a relaxation. We've shown that it's exact in a meaningful set of circumstances, and that we actually can write it all as a second order cone program. So that means we can really solve it at large scales. This is a more recent paper we just had accepted. This is led by Shuyao Tan, a PhD student in my group, who's in chemical engineering, actually. And there are actual other growth rates we can also represent as second order cone. You can take minimums, you can take some other combinations, but let's also keep in mind that these are populations of millions or billions of little cells that are growing. So the monod kinetics, it's extensively validated over time. It's established. The mu, max, and k have important physical meanings, but it's not computationally great because the kinetics are not concave. And it doesn't actually come from first principles. So there's nothing really sacred about it. So instead, one thing we can do is say, what if we just have generic growth data? We can just fit a general second order cone constraint. And we've got more parameters to work with. It turns out to be a non-convex optimization problem that does have partial second order cone structure. And it's a good fit for the convex concave procedure, which we use again later in this work. So this is just another way of saying we have some options even when those growth rates aren't what you want. Another question, what if the solution is not exact? So you do your relaxation and you find out that the variable t is way below the growth kinetics. But let's think about how our relaxation looks. In the case where we're just talking about monod and we said the growth rate, the biomass concentration was constant, well, the exact feasible set, which is non-convex, we say that the solution has to be on this curve in the ST space. The relaxation says we have to be in this dotted area, anything on or under the curve. Well, if we're not exact, that means we're somewhere down here. We can just add another linear constraint if we have some estimate on what the minimum and maximum can be. And doing so, we can really limit the degree of inexactness. We can go even further, actually. So this was a paper we wrote on state estimation, something called moving horizon state estimation, where we actually solve a sequence of second order cone programs to get a feasible solution. If we basically, this is again the convex concave procedure, and the interpretation of each step of this iterative algorithm is actually just taking this line and iteratively raising it until it just makes constant at a point. Until it just makes contact at a point. And that point where it's tangent is your feasible, potentially locally optimal, but still feasible solution. So I think that these are kind of a nice pair of catch-alls that even if monod or Contois is not doing what you want, you can still do an empirical fit. And if inexactness is really a problem, well, you can always throw a constraint like this in that's basically free computationally. And if you're willing to do 2 or 3 iterations of the convex concave procedure, you might be able to get a feasible or really close to feasible solution. Okay, so these are some preliminary numerical results. So I'm going to skip a few steps. These are in our follow-up paper, we basically did that development on a more general model where we had any number of concentrations, not just one substrate. So in this case, we had 5, that's biochemical oxygen demand, ammonia, nitrites and nitrates, and biomass. In some models, they have as many as 50 different concentrations. We can have multiple reactions, not just one in each chemostat. We also include dynamics. So in this model, we had about 1,300 time steps, 15 minutes each, so about 2 weeks. Now, if you've ever driven by a wastewater treatment plant, it's like the opposite timescale of power systems. You have like 1 million gallons of wastewater in your tank. The timescales are quite slow, actually. So we're this is a system that we've been working on from Paris because we've been talking with the Paris wastewater treatment utility, and it's not actually that big of a network. We're just looking at a subset of it. But I was telling Antoine It's a utility and it's French, so very slow to work with. So that we have a few new modeling components beyond what you saw. Instead of having just a biomass and substrate, we just have a generic process state. And we relate the different reactions to the growth of each of these concentrations via something called a stoichiometric matrix. So this is a generalization on the gradostat. However, all the hard parts, the network structure and the nonlinearities, we took care of those just in the gradostat. All this other stuff is just sort of repetitions of the same modeling elements. Now I called this a preliminary numerical results because we're pretending that we can actually allocate the biochemical oxygen demand in ammonia. Really what you would have control over is some valve positions that you might be able to open or close once a day and some pump speeds. Our objective is to minimize substrate concentrations, which means minimize untreated wastewater. And we have some constraints that roughly represent regulatory limits on what you're allowed to release into the environment. So really what we're just trying to do is throw in the right ingredients to prove that we can work on a problem of a realistic size and shape, even if it's not actually the real problem. One little note on how we put dynamics in. Remember the gradostat, we had differential equations. Before we set them to 0, now we just replace them with finite differences. And what we end up with is a copy of all the optimization variables in each time period, which are coupled by these constraints. And so all we end up with is, if you have t time periods, then you have t times as many optimization variables. Okay, so this is what the results look like. What you see here are the decisions, the amount of BOD and NH4 that's being sent to each of the tanks. Tank 1 in green is the most efficient, followed by tank 3. And what you see is tank 1 is getting the most, then tank 3, then tank 2. This problem had 145,000 variables. It took 17 minutes with Barobi. Most of that was pre-processing. And if we take a look at the concentrations in the plants, which is where we were actually applying the constraints, this is what we want to see at the optimal solution. Exact satisfaction of constraints, curves that don't look so simple that you think there might have been an analytical solution, but don't look choppy or noisy either. So it feels like we really did converge. And the last thing is that even though we do have conditions, even with the dynamics for exactness, they're a lot more complicated. And we didn't satisfy them perfectly here, but nonetheless, the solution was effectively exact up to just numerical effects. So we solved this dynamic optimization problem with tons of details, process states, stoichiometric matrix, and we were able to solve it at a very big scale. And even so, we still got lucky and ended up with the exact solution. And so stepping back, I don't mean to claim that we are ready to solve real problems in wastewater treatment, but as a convincing piece of evidence, I think we've shown that there was real value in doing the analysis of the problem. The relaxations are quite accurate, and they enabled us to solve problems at the scale that we need to get to. So let me talk briefly about the work that we're doing right now. So Shuyao, who I mentioned before, is the one carrying this work forward in her PhD. There's lots of uncertainty in wastewater. You can imagine you're trying to predict the weather. You're trying to predict what people are flushing down their toilet. And what's coming out of factories. So fundamentally, it makes sense to deal with uncertainty. And we're just looking at some basic chance constraint stuff. And she's also implementing some I think she's using alternate direction method of multipliers just as a first pass way to deal with the bilinearity, just to alternate which set of variables so that we can basically trade off between solving linear and second order cone programs. So that's, yeah, I would say that's something very interesting. On the wastewater side, there are still many more things to model. Biomass recirculation, aeration is a very expensive component. Modeling the energy for a more techno-economic analysis. And wastewater, this was a natural application as someone who works a lot on infrastructure anyway. And my collaborators these are fields they've worked in, but there are many other bioprocesses that are also similarly details on top of the gradostat in a sense. Finally, I'll mention I'm writing a paper now on metabolic networks because, let me go way far back. The monad function, the monad growth rate in metabolic networks, this exact same thing is called the Nicholas-Menten kinetics. Anybody ever heard of that? And they do all sorts of convex analysis just on the linear case in metabolic networks. And there's a particular optimization called flux balance analysis they use. And right now, we're trying to see what we can do to generalize that. And I think we have some other results. But it's just a field I know even less about since I'm technically a power systems guy. Okay, so let me see if there's anything else. Nope, that's it. Thank you for listening. Happy to take any questions.